I would like to move on to evaluate the partition function for the perfect gas. That's what we ultimately want to arrive at, the partition function for the perfect gas. And the first case for which I want to do that is the classical limit. And let's try to understand what the classical limit means, or when the classical limit is justified. A gas is classical, or you can treat a gas classically, if the distance between particles, the average distance between particles in your gas, is much larger than the wavelength of your particles. Well, strictly speaking, these are quantum particles, so they have associated with them, they have a certain wavelength and a certain uncertainty in their position. As long as this wavelength is small compared to the distance to the next particle, they won't overlap and they won't feel their quantum nature. What is the order of magnitude of the distance between particles? One rough measure is the following. We can take the total volume of the gas, divide by the number of particles in the gas, the total number of particles. This is, you can imagine that you take the total volume of your gas, divide by the number of particles, and then this gives you the volume that each individual particle in the gas has available for itself. It's sort of the personal bubble around one particle. And the typical length associated with this volume is the cubic root of that. That's a typical length scale that characterizes the distance between particles. The wavelength of a particle is given by Planck's constant divided by the momentum of the particle. Now, the momentum of the particle is related to its energy. It's the square root up to numerical factor of mass times kinetic energy. Now, when you have a gas at a certain temperature, T, then the temperature sets a typical energy scale, namely kT. We had seen this in previous examples. Remember the harmonic oscillator, for example, where the energy of a harmonic oscillator, the internal energy of a harmonic oscillator, scaled like kT. And the same holds true for a free gas. The typical energy of a particle in the gas scales like kT. So this scales like h bar over the square root of mkt. So in other words, this is again a rough heuristic argument, and I'm arguing with orders of magnitude here. As long as on the left-hand side this cubic root of V over n is much larger than on the right-hand side this h bar divided by square root of mkt, then you can say that the particles do not feel their quantum properties, because their extension due to their wavelength is much smaller than the distance to its neighbor. Let's check qualitatively when this is the case. The left-hand side becomes large when the density of particles is low. So this condition should be satisfied for low densities. When density is low, then n over v is small or v over n is large, so the left-hand side becomes large and the condition is satisfied. We can also look at the right-hand side and we can wonder, sort of at given density, so keeping the left-hand side fixed, we can ask, when does the right-hand side become small? Now the right-hand side scales like 1 over the square root of temperature, so the right-hand side becomes small when the temperature becomes large. So the condition is also satisfied when temperatures become high. The converse statement is to say that quantum effects and the quantum nature of particles becomes important when we have high density and or low temperature. And this links with my previous remark. We talked qualitatively about the behavior of bosons and fermions, that the distinction between bosons and fermions and the effects of quantum statistics, they become most pronounced at low temperatures. And here you have another argument for the validity of that statement, because the lower the temperature, the more likely you will violate this inequality and the more likely you will be outside the classical limit, so in the quantum regime. Let's make a little check of orders of magnitude and check plausibility. Let's consider a gas, a typical gas at room temperature. And let's check whether we can treat a typical gas at room temperature classically. What are some typical scales? The mass of the atoms or molecules. Let's say we have, so the mass of an individual atom, let's say we have of the order 10 nucleons, protons and neutrons. So the mass should be of the order 10 times U, which is the nucleon mass. That's of the order 10 to the minus 26 kilograms. That's a typical scale. The temperature is of the order, at room temperature, of the order 300 Kelvin. So together, this implies that the wavelength, the typical wavelength, let me call that lambda, the typical wavelength is roughly of the order 10 to the minus 11 meters, which is 0.1 angstrom. This is a very rough estimate for the typical wavelength. Compare this to the average distance between the particles. A typical order of magnitude for the number of atoms in your gas is Avogadro's number, so that's 6 times 10 to the 23 particles. And the volume, typical volume, 20 liters. And then we can calculate the cubic root of V over N. And this gives of the order 10 to the minus 9 meters, which are 10 angstrom. So we see that there's a difference in order of magnitude by a factor of the order 100. So indeed, with this very, very rough estimate, we see that indeed for a typical gas at room temperature, the average distance between particles is a lot larger by a factor roughly 100 than the typical wavelength of particles, and that suggests that we can work in the classical limit. And indeed, that's what experience tells us, that for gases at room temperature, we can describe them very well as classical gases. Let us consider the formula for the total number of particles. Remember, that was this integral over energies, level density, and then occupation factor. When we insert the level density that we found for non-relativistic particles in 3 dimensions, and we divide by the volume, then we get a formula for the particle density, the number of particles per volume. This is then proportional to mass of the particles to the power 3/2, that comes from the level density, divided by Planck's constant cubed. Then we have the integral from 0 to infinity d epsilon, and then we have the square root of epsilon from our formula for the level density, and we have the occupation factor f of epsilon. Substituting beta times epsilon equal to x, then this gives a square root of mass. Then we get a kt in front over h bar cubed, and then we have an integral dx, where x, we substituted that for beta times epsilon, and we have a square root of x, and the occupation factor we write in this form 1 over e to the x minus alpha plus or minus 1. Now look at this formula. We have on the left hand side we have n over v. On the right hand side we have in front of the integral this ratio, square root of mkt divided by h bar. This is the same expression that appeared in our classicality condition on the right hand side. It's the reciprocal of that. We have it's 1 over the wavelength. We said classically the cubic root of v over n is much larger than this wavelength. Or in other words, v over n is much larger than the wavelength cubed. Or n over v, the particle density, must be much smaller than the reciprocal of wavelength cubed. Now here in this formula, we have on the left hand side, we have the particle density, n over v. On the right hand side, in front of the integral, we have 1 over the wavelength cubed. We said that classically, the left hand side must be, n over v must be much smaller than this factor in front of the integral. And this implies that the integral itself, this integral, this must be much smaller than 1. The classicality condition implies that this integral must be much smaller than 1. When is this integral much smaller than 1? It's much smaller than 1 if e to the alpha is much smaller than 1. So alpha is negative, and it's very negative. It has a large absolute value. It's very negative. This ensures that the exponent that features in the denominator is very large. The x minus alpha is very large. So the occupation factor becomes very small. Okay, so you have this condition, e to the alpha must be much smaller than 1. And this implies that alpha must be negative and also mu must be very negative. If e to the alpha is much smaller than 1, this means that e to the x minus alpha is very large and dominates over the plus or minus 1. So in this limit, we can omit the plus or minus 1. Therefore, the distinction between fermions and bosons disappears. Yeah? Because in this limit, we can omit the plus minus 1, and hence the distinguishing feature, the distinguish between bosons and fermions. And this finally allows us to write down the classical grand canonical partition function, or the log of it, as a function of beta, alpha, and volume. When we look at the formula for the grand canonical partition function in the continuum limit, the formula for the grand canonical partition function has this form below in the last line. And we learned in the classical limit we can omit the plus or minus 1. And therefore, the 1 over this occupation factor simply becomes e to the alpha times e to the minus x. And we can take the e to the alpha in front of the integral. And what remains is the integral over e to the minus x, and then the number of levels up to x over beta. And then we can, at this point, we can use the results that we found for non-relativistic particles in 3 dimensions for the number of levels, for the curly n. That went like the volume times energy to the power 3/2. Now the argument is x over beta, so this will go like, we have the volume, and this will go like beta to the minus 3/2. Yeah, so n of epsilon goes like epsilon to the power 3/2 we found for a 3D particle. Now we have n of x over beta, and this goes like beta to the minus 3/2. We can take that also in front of the integral, and then what remains is an integral over x, e to the minus x, and then x to the power 3/2, and from 0 to infinity, and this gives some number, and which we absorb in this proportionality sign. But the dependence on the thermodynamic variables is given here. It's e to the alpha times volume times beta to the minus 3/2. So we found on the previous page that the log of the grand canonical partition function goes like e to the alpha volume beta to the minus 3/2 for a classical gas. And now it's all very quick. The total number of particles, we know from our general framework, is the partial with respect to alpha of the log of the grand canonical partition function. Now, this log of the grand canonical partition function goes like e to the alpha, the derivative of e to the alpha is e to the alpha. So this is equal to the log of the partition function. N is equal to the log of the partition function. Secondly, we know the partial derivative of the log of the partition function with respect to volume We know from our general framework that this gives beta times the pressure. Now, how does the log of the partition function depend on volume? It's simply proportional to volume. So when you take the derivative with respect to volume, it's tantamount to dividing by volume. So this is the same as the log of the partition function divided by v. The log of the partition function we found previously is equal to the particle number. So this is the same as n over v. You recognize we have beta times p equals n over v. Beta is 1 over kt. We can multiply by kt, or we can multiply by v. And we find the ideal gas law. P times v equals nkt. That's the ideal gas law. And the derivation is extremely simple. Once you have the partition function, it follows immediately. Then we can look at the internal energy of the gas. The internal energy, by our general formalism, is minus the partial with respect to beta of the log of the partition function. The log of the partition function goes like beta to the minus 3/2. So when we take the derivative, this will give us a factor minus 3/2. And we have a minus sign in front. So effectively this gives a 3/2. And then we have log of the partition function divided by beta. Beta is 1 over kt, and the log of the partition function is n, is the particle number. So this is equal to 3/2 nkt. Again, a formula that you have probably seen before, and it follows in a straightforward manner from the log of the partition function. You can combine the last two equations, the ideal gas law and the formula for the internal energy. You can replace the nkt in the internal energy by P times volume from the ideal gas law, and you find that the internal energy is 3/2 pressure times the volume. One interesting aspect will be to see for the quantum gases whether these equations still hold or whether they are modified in the quantum case.